Hello, this is Wei. In this talk, I will be introducing you to the problem of separating polygonal sets with a minimal number of lines. To introduce the problem and motivate our study, many government, military, and industrial facilities or museums have areas with different levels of clearance. It may be desirable to monitor the traffic flow among different areas. For example, for hosting an event, we may want to quickly set up line-of-sight sensor barriers that can separate these three sets of building blocks colored in orange, green, and purple. And there are some additional building blocks that we do not care about, colored in gray. A natural question that arises is, what is the minimal number of such barriers, and how to place them? For this particular problem, we may use 8 barrier lines to complete the separation task. To formally define the barrier forming problem, there is a 2D polygonal workspace containing k sets of polygonal regions, S1 to Sk, together with a set of polygonal obstacles. We are interested in finding the minimal number of straight-line barriers to separate S1 to Sk in a pairwise manner. Our study is inspired by the problem of barrier coverage that finds the minimum total length of barriers to separate two sets of regions. In computational geometry, people have studied similar problems but focus less on practical algorithms, which is the focus of our study. This work is also partly inspired by the study of pursuit evasion games, in which a moving flashlight or beam is often used to search the environment. From the results of related study in computational geometry, we know that even for separating two sets of points in the plane with the minimal number of lines, it can be hard. As a result, the barrier forming problem we studied in this paper is also at least NP hard. While there can be an infinite number of choices in selecting barrier candidates, we show that any barrier sets may be converted to one containing tangents or bitangents. We prove that for separating point sets with polygonal obstacles, using tangents and bitangents are both complete to find an optimal solution. That is, there exists optimal solution with a minimal number of line barriers that are all tangents or all bitangents. We also show that for separating polygonal sets, using only bitangents can guarantee a two optimal solution. For a finite set of candidate line segments, for example, the bitangents of the workspace that can have at most a quadratic number, we propose to use integer programming to solve this problem. To achieve this, we decompose the workspace using the candidate barriers, after which we can encode the constraints and objectives of the optimal solution using linear constraints. Theoretically, bitangents are optimal for separating point sets and two optimal for separating polygonal sets. This property is preserved by our proposed algorithm. We show here a few example solutions computed by our algorithm, which usually solves instances with around 10 object and around 50 object vertices in under 2 minutes. As we are using integer programming, the variation of the time cost is very high, and we are currently working on further improving the efficiency. Thank you for listening.